Hi everyone, my name is Anna Vettoruzzo and welcome back to our machine learning course. Today's lecture is all about advanced LLM capabilities through RAG and tool usage. In particular, we will first start with a general overview about the agents, and then we will move towards agentic AI, retrieval augmented generation, tool usage, and finally, the MCP protocol. But let's get started with a short recap about the previous lecture. In particular, we saw that large language models are usually transformer-based architecture that have been pre-trained on a massive amount of data in order to learn some general knowledge, and then they are instruction-tuned for a specific task. They usually work by generating some output text, given some inputs instruction, for instance, and they function through next token prediction. But I'm pretty sure that despite LLM, recently you have heard about agentic AI, and you may end up reading some of this article that I posted here. For instance, that AI agents are helping in healthcare application, bringing a step towards smarter preventive medicine. Or maybe that an AI agent publish a hit piece on someone, generating a lot of privacy issue. Or even worse, maybe that AI coding agents wiped out the user data after making cascading of mistakes. And while encountering these articles, you might have wondered, what is agentic AI? What is an agent in this context? So an agent is usually defined as an intelligent system that interacts with environments. So you can see that we have an agent that here is represented with a robot, but not limited to this, that generate some actions. These actions will modify the environment, and we will get back some observation from these environments. This observation will be internalized inside the agent who will use them to make a decision about the next action to take. But what does intelligence mean? And there is actually no wrong answer to this. I listed here some possible answers, but feel free to stop the video and think about what intelligence means for you. In my idea, one possible answer for intelligence is that the agent knows about the cause and effects, or that it has the ability to generalize to out-of-domain scenarios that it has never seen before. Or again, it can understand their words and be able to interact with it. Or finally, it can remember and also improve from experiences. But let's look at the agent framework. So usually the agent framework consists of 5 different components. At the center of the framework, we have the agent, which acts as a sort of a brain or coordinator. A user, like a person, you for instance, you may ask like a question to the agent, and the agent will then exploit one of the free modules that it has available to provide the correct answer. Or it might even like use all the three of them based on how complex the answer is. These modules are the planning modules, which breaks down the steps to solve the problem in easier steps. The memory module that stores some past thoughts, actions, and also observation, such that the agent can quickly retrieve them instead of regenerating the same. And finally, also some tools that enable the agents to interact with the external environment and, for instance, retrieving some real-world or very recent information. It's also very important to notice that usually the memory of an agent is divided into 2 parts. We have a short-term memory, which is also called the context window, where the agent's current situation are stored. And a long-term memory, which is usually much larger, and they store the past thoughts and the behavior in an external buffer that needs to be called once some information from this memory is necessary. So to summarize, if we want to list here the three requirements for successful agents, we can say that an agent should have a cognition part, meaning that it should be able to reason, to plan, and also to represent the environment that surrounds it. It should be able to understand the environment, so to perceive what's happening around it. And finally, also to use some tool and communication strategies to interact with the environment. But you can consider many different type of agents. For instance, even a CIA agent can have some of these characteristics. But in this lecture here, we will focus on large language model agents. The only difference with the previous one is that the agent now it has an LLM backbone, and it usually interacts with the environment through prompts and action or observation space, usually in the form of text, but this is not restricted to it. So let me just show you some examples about possible agents, and let's go through them together to see whether each of these examples is indeed an agent or not. For instance, let's consider the first definition here, where we have an LLM system that browses the web. We can see that this is indeed an agent because it's a system that can take in input some user prompts. It can reason about what the web search needs to be. It can then interact with the environment by searching the web and retrieving the correct information. If instead we ask ourselves, what about an LLM like GPT-01 that has complex reasoning? Can this be considered an agent? And the answer is actually no, because this LLM has the ability to reason, but it has no way to interact with the surrounding environment. The third example instead is an LLM that takes in input some natural language, so some text. It plans a solution, and for instance, it applies some changes to a web app or a repository. And if you remember about the requirements for successful agents, we can find the three of them in this agent description. Indeed, these agents can plan a solution, so divide the problem into small steps, reason about each of these steps, and also interact with the environment to change, for instance, a web app or a repository. And very similarly, also a coding agent can identify some bug or create a new branch or write some code or run some tests. And as actually the description is already telling you here, even this one can be considered as an agent. And finally, let's assume that we have a large language model that takes in input some English text and performs some kind of translation to output the French translation of this text. And if you think about it, here there is no real reasoning going on and no interaction with the environment. So the answer is no, this is not an LLM agent. So I hope that from this example, it is a bit more clear what we refer to when we talk about agentic AI. But as we also saw, at the main backbone of LLM agents is an LLM model, right? So actually an agent can have the same weaknesses or challenges that vanilla LLMs already have. We saw some of these weaknesses in the previous lecture, but let me just repeat them here. So recent LLMs have limited reasoning abilities. They also have a static knowledge with a cutoff phase that depends on when the pre-trained data were collected. The knowledge of vanilla LLMs is also restricted to the training data. So let's assume that we are a company and we have some private data that we cannot share with the rest of the world. And one thing that we can do is to fine-tune our model on our private data and store the model locally, right? But actually, this is good in some sense. But if we update our private data, we should do the post-training phase once more, which is very costly. And most of the time is not what we want to do. Another weaknesses of vanilla LLMs is that by themselves, they cannot perform any action. So they cannot really interact with the environment by, for instance, searching the web or pushing to a GitHub repository. And finally, they are pretty hard to evaluate. But in the rest of this lecture, we will mostly focus on the three bolded weaknesses, and then we will see different methods that researchers have developed to address them. Let's start with RAG, which stands for Retrieval Augmented Generation. And in particular, the motivation of RAG is because LLM only know about data that have been used for pre-training or fine-tuning. So every LLM has a knowledge cutoff date, meaning that it cannot access to recent information. Plus, as in the example that I did before, if there is any private information that is stored in some database that we have locally in our company clouds, we also want to make sure that we are able to retrieve the information from here. So for instance, if you just search on the web GPT 5.2 or Llama 4, that are two very recent models, you will find some information about these knowledge cutoff dates. And in particular, this means that after August 2025 for GPT 5.2 and August 2024 for Llama 4, the model doesn't know anything about the recent information. So you might wonder, how can we address this? And one very naive approach is that we could add all the useful information we need in the input prompt, and then pass all these huge prompts to the LLM in order to generate the answer to our query. But of course, this has several challenges. First of all, the context window, so the number of tokens that you can have in your input prompts, is usually limited to hundreds of thousands of tokens. Second, the LLM gets distracted by useless information, meaning that if you add all the available information in the input prompts, the LLM might retrieve and might reuse some information that are actually not needed for answering your user query. And finally, most of the proprietary model like GPT or even Gemini, they have a price per input output token. So ideally, you want to keep the number of tokens in input and output as small as possible. So one smarter approach that researchers developed in the last few years is called retrieval augmented generation, or RAG in short. The idea of this approach is well represented in this picture in the slides. And you can see that instead of simply querying an LLM with a query inputs and generate an answer, we have an additional step here, because the query inputs is used to retrieve some important information or important documents for a database. And this information is then used to augment the query inputs in order to provide more information to the LLM to generate the correct answer. And the RAG is usually divided into three different steps. So the first step is probably the most important one for the final performance, and is the one that we will focus more on this lecture, and is the retrieval phase, where we want to retrieve only the relevant document or the relevant information that can help the LLM to answer our user query. In the second step, instead, we have the augmentation phase, in which we append this retrieve information to our user query. And finally, in the generation step, we just provide an input, the augmented prompt to the LLM, and then we generate a response. But let's have a look at the first phase. As I was saying before, the first phase is actually the more important for the final performance. And it is usually divided into two parts. We have a pre-processing phase and the real retrieval phase. So in the pre-processing phase, we first collect the documents that we need to support our user query. And we store them, usually these are stored in a database, or they can also be simply downloaded from the web and stored in a folder. Second of all, we have all these documents, and what we want to do is to divide them into chunks. And usually a chunk consists of hundreds of tokens, but is up to the developer to define the chunk size and the overlap between chunks. Because most of the time, there are some common tokens between two subsequent chunks. And finally, we have an encoder model that could be, for instance, a pre-trained transformer encoder such as BERT that maps each chunk into an embedding vector. In the retrieval phase, instead, what we want to do is to select the relevant candidates. And remember that we want only the candidates chunks that actually contain some information that are useful for the user query. To select these candidates, what we do is that we embed each query, each chunk into an embedding vector, as we saw before, but we also embed the query into an embedding vector using the same encoder model. Once we do this, we compute the cosine similarity for each pair of query and the chunk that we have available. And finally, we can rank the chunks based on this similarity for the final relevance score. This is one simple method that can be applied for the retrieval phase, but there are many more that you can find by checking this reference that I put here in the slides. Let's now have a look at some Python codes on how we can have and implement a RAG pipeline. So there are many different libraries that can be used for RAG applications. But in these codes, we will focus on the Llama index framework. And in particular, we will also use the Llama library to run LLMs locally. Okay, so let's start with some import statements and then the definition of the generation model, so the LLM model that we want to use, and the encoder model. We also need to define some hyperparameters and Ollama settings. In particular, here is important to notice that we have the maximum number of tokens, of new tokens, that is set to 4096. The temperature, the size of the context window, so how many tokens we can input into the model, and then some Ollama settings. Once this is done, we also need to tell the Llama index library which generation model and which embedding model or encoder model we want to use. And we can do this simply by modifying the settings method from the Llama index library. Then, as usual, we need to select and load a dataset. And for this specific example, we use this RAG dataset 12K example, but we only extract a very small subset with the 200 samples just for simplicity and for running the code faster. The first thing that we need to do once we loaded this dataset, that for instance, it was loaded from Hugging Face, is to convert it into a format that is readable by Llama Index. And this can be done simply by iterating over the training data and store each document with this document class from Llama Index. And in particular, we also need to tell where the text is. And in our case, it is inside the context attributes. And we can also add some metadata, such as the original question and the original answer, although this is not necessary. Once we do that, then we can really step into implementing the RAG pipeline. And as we saw before, the first step of the RAG pipeline is the pre-processing phase. So if you remember in the pre-processing phase, the idea is that we want to divide our documents into overlapping chunks and then use an encoder model to encode each chunk into an embedding vector. So with the sentence splitter method from the Llama Index library, we can define how we want to split our documents into chunks. In particular, here we have selected a chunk size equal to 256 and an overlap of 20. And then we can simply use this vector store index with this text splitter method that we have defined before to chunk the documents into different chunks. And finally, we just save it in a persistent directory storage just for easy retrieval. Then we need to define how we want to do the retrieval phase. And if you remember, in the retrieval phase, the idea is that we want to use a method to retrieve or to select the most informative documents based on the user query. And in this specific example, we just picked the top 3 chunks, which are the chunks with the highest similarity to the user query. And then actually this is it, because then we can simply ask a question such as, what is one of the most difficult things for yoga teachers after teaching a class? And we can just query our query engine with this test question to get a response. So remember that at the beginning of this code implementation, we explicitly told the Llama Index library which generation model and which encoder model we wanted to use. So when we run this query method from the query engine, actually Llama Index already knows the encoder model that we want to use and which generation model we want to use. So we don't need to do anything else. And then you can see on the bottom of this slide here, the generated answer, which is the most difficult thing for yoga teachers after teaching a class is to help students find their own path and develop their own spiritual growth. And then you can also print the top 3 retrieved sources, meaning the chunks that have been retrieved because of the highest similarity with the user query. And if you go through them, you can see that at least some of them have some connection with the generated answer. Cool. But now we know how to implement a RAG pipeline and we know how the RAG works. But what are the challenges of RAG and how can we address them? So RAG needs a very large context window. And this is because in the final stage, in the second stage, sorry, of the RAG pipeline, if you remember before, we needed to augment the user query with the retrieve information. So one way that you can address this is to retrieve only the like top two or top three sources. Of course, if you increase the number of retrieve chunks, then the context window will quickly explode. The second point is that the retrieval phase in step one plays a crucial role, as I said before, and because it needs to maximize the diversity of the documents without providing useless information. And this is controlled with the parameters that the developer needs to define, which are the chunk overlap and the chunk size. The third point is that LLMs struggle to capture information in the middle of the context window. So actually the retrieve information placement needs to be optimized. And there is like quite a lot of research papers that try to explore what is the optimal place for the retrieve documents. And finally, the data cleaning and the formatting is challenging. So until now, we have seen how we can increase the capability of an LLM by let it retrieve some useful information from some database and use this information to produce a more accurate response. But this is not the only way to make an LLM interact with the surrounding environment. For instance, if I ask an LLM what is the prime factorization of this large number here, this requires some computation, probably by using some Python code, for instance, which is not directly available from the pre-training phase of the LLM, and then not even from RAG, of course. Or another example is that I would like to know what is the current weather in Eindhoven, for instance, and this requires some real-time data, meaning that the LLM needs to get access to some external API that collects some weather information. So in order to do this, one thing that we can do is to support LLM with tool usage. You might wonder, what is a tool? So a tool is a quite broad term, but usually the definition that we assign to tool in this specific context is that a tool is an external function or API that allows the LLM to interact with the environment. So a tool usually has three important characteristics. The first one is that it is external to the LLM. Indeed, like this is part of the environment per se. It has a function interface that is callable with the inputs-output parameters. So in other words, it resembles like the functions that you usually use in Python, for instance. And it is executable as a program. Let's have a look at different categories and different examples of tools that are usually integrated within the latest LLM. So there are some tools that provide some knowledge access, such as a retriever, which is very similar to what we already described during the RAG explanation phase. But it can also be an SQL executor or a search engine, a web search engine, for instance. Then we have some tools that can calculate some formula or use a Python interpreter, or again, play around with some spreadsheets. We have some tools, as I mentioned before, that can get some weather information. They can get the location of a restaurant, for instance. They can fetch events from a calendar, or again, write, verify, or send some emails. There are also tools that deal with non-textual modalities, such as we can ask Spotify to play some music, or we can ask some question about an image that we find on the web, or again, we can ask to delete some images, for instance. And finally, of course, there are tools that support question and answering, translation, or other special skills language models. But how tool works in practice? So the idea is that you can see the small steps here with the blue number, right? So a user query an LLM asking, for instance, what's the current temperature in Milan? And the LLM given this query recognize that it doesn't have this information, but it can, for instance, call a tool that is called get weather, just passing as inputs the information about the location, which is Milan, Italy. And the clients can interact with a weather API that is maybe available on the web, just to retrieve the information about the current weather in Milan, which of course is not the 32 degrees, but just for the sake of this exercise is fine. And then like the client can give this information back to the LLM. The LLM can modify it and integrate it into a response that looks like as an answer. And then it provides an input to the user, the answer, the current temperature in Milan, Italy is 32 degrees. So if we want to implement this in Python, we can follow all these steps one by one, and we will see now how to do it. In particular, we will implement a function called getCurrentWeather, and we will integrate it within an LLM that supports tool calling. It is very important for this exercise to select an LLM that can support tool calling already, so that it has been trained for tool calling user and tool usage. And you can find a list of these LLMs in this link that is in the slides. So as usual, let's start with some downloads and some imports. So for instance, you can see here that we are using Olama once again, just to run the model locally. And in particular, we are using Llama 3.2, 1 billion. Once we have downloaded all the required packages and imported all the libraries, we need to define a function. Indeed, if you remember from some previous slides, we said that one of the characteristics of a tool is that it needs to be defined with some function with inputs and outputs. And in particular, in this specific example, we define this getCurrentWeather function, where we provide in input the location and maybe some additional arguments as well. And we simply output a string just for the sake of simplicity. But of course, in production, this function should actually call a real weather API and then output the information from this API. Then one very important thing to do is that we need to create a function schema for this function. And this function schema is simply a standard that was introduced from OpenAI, if I'm not wrong, and it is used to teach the LLM how to use the tool. So as you can see, you need to define the name of your function, a description, and the parameters that it takes in inputs. Then you need to write a prompt that you can use to query your LLM, such as what's the weather in Amsterdam right now. And you can see here that we are also modifying the system prompt actually. So there is a small difference between the system prompt and the user prompt because the system prompt provides some general information to the LLM about what its behavior should be, while the user prompt is the real question that we want to ask. So for the system prompt, we are telling our LLM that you are a helpful assistant, and when users ask about current weather, use the get current weather function to get accurate data. This is an example, of course. Feel free to play with it and modify it as you want. And then once we created these messages and we have our weather tool, we can simply use the do an API call. This is using, for instance, OpenAI API, but you can use other APIs if you prefer. And then we need to have a look at the response that we will have. So if you just query an LLM with a normal LLM that cannot support the tool usage, without a question such as what is the current weather in Amsterdam, it will probably reply by saying, I don't have access to real-time data, I'm sorry. But in this specific case, instead, our LLM, which is a Llama 3.21b, if I remember correctly, is recognizing that we need the tool that we implemented and is outputting this chat completion message, in which if you look at the last parameter, which is tool calls, you can clearly see that our model recognized that it needs to call the function get current weather with as input Amsterdam NL. So this is it actually. Once we have it, we just need to do some cleaning and we define this function here just to create the response and make it readable for us. And you can see that the answer when I was running this code was windy condition with a high of 5 degrees in Amsterdam, Netherlands. And if you remember, this is indeed what the get current weather function was providing as output. I also want to clarify here that the generation process of an LLM is always stochastic. So if you also try to run these codes, you might end up having different results, or it might happen that your model is calling a different tool, maybe because some weather tool-based information was already implemented inside the Llama training, or it might end up not recognizing the tool at all that you implemented. So just try to run it multiple times. And we will see in the next few slides how we can optimize tool usage by training our model with it. So from now on, we will look at how we can train our model or fine-tune our model or just prompt our model to use a tool. The first method that we can apply is to do some post-training on a pre-trained model by collecting different SFT pairs, so supervised fine-tuning pairs, and then use these pairs of input and output in order to fine-tune our model with one of the techniques that we saw in the previous lecture. The difficult part here is that we need to collect a lot of these pairs of input-output, and in particular, we need to do that twice. Once for the tool prediction, so when we ask our query to the LLM, we need to make sure that our LLM can recognize that it needs a tool. And we need to try with multiple different questions and also a lot of different tools in order to have millions or even billions of pairs of data that we can use for post-training our model. But then we also need to have some pairs for the response generation, because if you remember correctly, once we get our answer from the external API that we want to use, the LLM actually needs to take this answer together with the user query and create a response that that is in a text-based format, and also it is user-friendly. So we need also to collect a lot of input-output pairs that contain the whole conversation history, as you can see here. So if you are a student and you are doing, let's say, your machine learning assignments, you might wonder if this is really necessary, because of course this requires a lot of time, both for data collection, but also for post-training, and also a lot of computational resources. So the answer is that there is actually a more efficient method to do that, and this is through prompting. So the idea is that we can actually embed some our tool definition and also an explanation on how to use this tool inside the input prompt, and then let the model figure out how to exploit this information. So you can see here, for instance, that our input prompts now consist of the function API definition. So for instance, our get current weather function we implemented before. Then we have a detailed explanation on how to use this function. And then we have our user query, that is, what's the temperature in Milan? The problem is that how can we write this detailed explanation on how to use this tool? Because if we want to write this explanation every time that we query our model, this is very time consuming and also difficult from the human point of view, because it's difficult to validate what is a good explanation for the model. So one idea is to use a few-shot learning, meaning that we can provide a few examples to the model of function API, an explanation of how to use it, and the inputs and the output that we are expecting. And then we let the model figure out how to answer to our last user query based on the previous examples. This is very simple and also very powerful, and usually like 2-3 examples are enough, but it lacks generalization to unseen examples. And you can see that the context window, so the number of input tokens that we want to use in our inputs prompt, can quickly become very, very large. So what people are usually using right now is another approach, meaning that they usually ask another powerful model, which usually is a reasoning model, to write a detailed explanation for you. So what they do is that they have this model that have been fine-tuned on a lot of pairs, and they have been fine-tuned just to extract some useful detail from the function API in order to address a user query. So I hope that is clear what a tool is and how we can implement it, the tool usage methodology in practice. But what I want to highlight is that in this lecture, we focused on a single tool. But what happened in practice is that we usually have many tools. So the benefits of having many tools for many different action and interaction with the environment is that the LLMs become very powerful. It can interact with the surrounding environments in many different ways. And in this way, we can also overcome the knowledge cutoff limitation. On the other hand, there are three challenges that having many tools can create. The first one is that the more tool we have and more difficult it is to retrieve the correct one for the LLM, which might result in a decrease in the performance. Then the context length. So the size of the context window is usually finite. And meaning that if we have a lot of tools and we have a lot of tool definition and also a lot of detailed explanation in there, we can quickly reach the limits, meaning that this approach is not scalable with the number of tools. And finally, of course, if we need to define this tool manually, this requires also a lot of work. So there are actually some methods that have been proposed in the literature that try to address this problem. And one idea that is pretty simple but also pretty effective can be found in the paper that I linked it here in the slides. The idea is that instead of just providing an input to the LLM, all the tools that are available, we want to use a router that can be another LLM or even like a simple encoder model plus some similarity measure in order to select which tool is which subset of tools is necessary and like more likely to be used based on the user query. And then we provide an input to the LLM only the user query, of course, and the subset of selected tools, and we generate a response. Cool. So I encourage you to actually check more about tool usage. I added a few references in the last slides that we will see now in a bit. But there are also a lot of like recent interesting paper that you can find online. So feel free to check them out. Finally, to conclude this lecture, I would like to introduce you to MCP, which stands for Model Context Protocol. And this is an open source standard for connecting AI models to external data and tools. So the idea is that instead of manually handling the orchestration of multiple tools with an LLM, we actually let this MCP to take care of this. So MCP usually consists of a client-server architecture with the following structure. So we have an MCP host that is the application where the AI model is running. And this could be an IDE, but also a desktop application such as Claude Desktop. And within this MCP host, we usually have our model, or at least some link to this model, and an MCP client. So the MCP client is a component that actually take care of the connection between the model and the servers. And then we will see in a while what the server is. And the client handles sending some requests to the from the model to the server and receiving data from these external sources or servers and bring it back to the model. So we have talked about MCP server, but what these actually are. So you can see here that I added some small icons such as GitHub, Slack, or an external database. And an MCP server is indeed a program or connector that receives the request from the MCP client. And then it does something. For instance, in GitHub, it might create a new branch, or in Slack, it might like write a message, or it can retrieve some information, and it responds accordingly. So it provides a feedback to the MCP client, either with some information or by saying, hey, I created the new branch in GitHub. And finally, we also have this data source or service, which is not part of the MCP itself, but it's the actual source of information or action that the MCP server interacts with. So for instance, in this example here, this service might be GitHub or Slack or this database of information. So the good thing, and the reason why everyone recently is using MCP, is that to build a new MCP server, we can simply implement the free key primitives, which are the prompt template, the resources, and the tools definition. So this means that if you have an LLM that supports the MCP, the model context protocol, and you want to add a new tool, you want to create a new tool, you can simply implement the free function that you can see here in the slides. And this is everything you need to do, because then the MCP handles all the interconnection. So let's have a look at this free function. So we need to define the prompt and decorate this function with this mcp.prompt decorator. Then we need to define the resources, meaning that we need to define where for instance, the API or where the directory with the contacts is. And finally, we need to define the tools, such as write an email draft. So you can see that this is very simple and doesn't require a lot of work from the developer side. And that's why more and more people nowadays are using MCP for their application. So the benefits of MCP is that there is a unique standard that everyone can use, and almost all models that support tool calling are using. It makes the context sharing and the tool interoperability easier, because as I said before, you can simply implement the three function for each new tool that you want to integrate. And it can then efficiently handle multiple tools and also data repositories. Great. So in this lecture, just to do a quick recap, we saw the definition of an LLM agent. We saw what are the drawbacks of vanilla LLMs, and how can we move from vanilla LLMs to LLM agents. And in particular, to do that, we saw retrieval augmented generation. That is a technique that allows us to retrieve some recent or private information and use it to augment the user query and get a better answer. But we also saw how to integrate tools with our LLM to let the LLM do many different things and interact with environments. However, there are still several challenges for LLM agents, such as they have quite a lot of hallucination and also security risk. For instance, we saw in the first slide of this presentation that one coding agent deletes all the data for a user just because of some mistakes. So please, use the LLM agents in a good way. Always validate what they are doing and make sure that they have no access to your private information. Then some other challenges is that the reasoning abilities of LLM and then also LLM agents are still a bottleneck, and the evaluation is challenging. But of course, there are different steps that researchers are looking into in order to improve these challenges. The first one is the multi-agent orchestration. So you might have heard recently that there is also sort of a social media for agents where different agents can interact. And for instance, they suggest to build a new religion for them. So this is indeed where the new research direction is going. Then the second step is human in the loop approaches. This means that researchers would like to integrate human reasoning or human validation within the pipeline in order to avoid hallucination and the security risk that we were talking before. And finally, of course, we need the better evaluation benchmarks. Great. I want to conclude by leaving to you some useful resources that you can check. And as I said before, this topic is very, very recent, and there are new papers coming out every day, but even like every hour. So feel free to search online in order to learn more. Thank you so much for listening, and see you soon.